Hello folks, and welcome to another segment of Working with Mr. Anderson on your physics homework. Now, this particular problem we're looking at is from the horizontal projectile motion assignment, all right? And I'm looking at problem number 1, which deals with a movie director wanting to shoot a scene where a stunt dummy is dropped from an airplane into a swimming pool, okay? And there seems to be a little bit of confusion on how to diagram this problem. And like we've talked about before, diagramming is one of the most difficult parts of physics, it seems like, for a lot of us right now. And as I've said before, practice makes perfect. So here's something to keep in mind about this. Check out this diagram from your physics textbook. If you check on page 102 of your physics textbook, you'll see this diagram where we have an airplane dropping a ball, all right? Now notice how when you're looking at the overhead view, relative to the airplane, it looks like the ball isn't moving at all. Yes, it's being dropped down, but it's moving at the same speed because you have no initial acceleration of this ball, just like horizontal projectile motion. But when you look at the undercarriage from the side view, as you drop the ball gets further and further down, and then it will hit the target, okay? So if we're looking at a diagram of what this particular problem looks like, I guess more of a picture than a diagram, if you have the dummy being dropped, the dummy is going like this. When the plane releases it, the plane's going to be following along this path, all along the path of the plane, okay, where the dummy will be dropped. It's dropped here, has that initial speed, and the reason why it's falling down at all is because of that acceleration due to gravity, okay? So keep that in mind. This is still just a horizontal projectile motion problem. It's its initial speed from the plane. It's traveling at the same speed of the plane the whole time because we're ignoring air resistance, okay? And it is dropping at that acceleration of negative 9.81 meters per second squared that we're used to, all right? So in this particular diagram, what you could say that we're looking at is just that normal triangle that we like to put in, okay? That triangle, and you could make this your triangle like that, but your dotted line follows that parabola like we've talked about, okay? So here are a few things that we know, all right? We know that the plane is 10.0 meters above the ground, okay? That's our delta y. And we know that the speed of the plane, all right, that's the x component of it, is 22.5 meters per second, okay? And the director wants to know when the plane should drop the dummy to make sure it lands right there. So we're trying to find our delta x in this particular problem, okay? And one other thing that we know as well too, as in with any of these horizontal projectile motion problems, is that our acceleration in the y is that negative 9.81 meters per second squared like we talked about, okay? So what we want to look at here first is saying, okay, since we're trying to solve for our x, we know that velocity equals your delta x over your delta t, okay? And when we're changing to our x variables, we can say our speed in the x, which is also equal to our initial speed in the x because the speed stays constant in the x component throughout this whole problem, in any horizontal projectile motion problem, we get delta x over delta t. So to solve for our delta x here, it looks like we're going to need our delta t, okay? And so if we look at the other kinematics equation that we've used for y, and we'll change our to our y variables here in just a moment. We have our delta x equals, what is that? It's, oh, I know you're yelling at me. Okay, here it's vi delta t plus 1/2 acceleration in your delta t squared. And I think they put that in parentheses, right? Okay, so here's the thing. Let's go ahead and change to our y variables. So delta x turns into delta y. And then our initial speed becomes initial speed in the y. Delta t is still just delta t. It doesn't matter if it's x or y component that we're looking at. Still 1/2 acceleration in the y. And again, we have our delta t over here squared. Now remember, for any object experiencing horizontal projectile motion, the initial speed in the y is 0, just like we've talked about in class. So since that's 0, that means that 0 times any time, it doesn't matter what it is going to be 0 as well. So this is gone. When you rewrite the equation, it's delta y equals 1/2 acceleration in the y, then your delta t squared, okay? So we've got this equation in. Do we know our delta y? Oh yeah, heck yeah we do. We've got it right over here. 1/2, do we know our acceleration in the y? Oh yeah, we've got that guy as well. So we're ready to go ahead and set this equation up, both of these equations, okay? So what we're going to need to do is solve for our delta t, okay? Now with the algebraic manipulation, here's what you're going to be seeing in this case. We need to get our delta t by itself. So that means we need to divide by 1/2 and our acceleration in the y. And whatever you do to one side of the equation, you've got to do to the other. So remember, when you divide by 1/2, that's the same as multiplying by 2. So I'll rewrite that to clean it up here in just one moment. So over here on the right-hand side of the equation, these guys are gone. They cancel out, okay? So let's rewrite it and clean this up. And I'm going to go ahead and flip this equation too, because I usually like to have the variable that I'm solving for on the left-hand side. That's kind of me, okay? So when we rewrite this, it becomes our delta t squared. If you want to still put that in parentheses, you can. I'm just getting rid of it now since it's a isolated variable there, and I know it's still squared, equals, because that 1/2, dividing by 1/2 is the same as multiplying by 2, so it's 2 times your delta y divided by your acceleration in the y. Okay. Oh, and by the way, something else I forgot to do that maybe you were probably thinking of it. If you were, awesome. I forgot to put the negative sign on my delta y up here in this problem that I was initially starting with. Because remember, the reason why this is negative 10.0 meters is because we're referencing it, we're focusing our attention on the dummy that's being dropped in this problem. Okay. So here's what we're looking at, and then it's going from down here. So it's heading down, a negative 10, okay? So that should be a negative 10 in your y displacement, alrighty? Now, anyway, back to this problem. I was just thinking of that, popped up in my head. To get t by itself, delta t, since this is squared, we need to do the opposite of squared, which is square root. And then again, whatever you do to one side of the equation, you have to do the other. The square and the square root cancel each other out. So you get this equation, delta t equals the square root of 2 delta y over the acceleration a. Okay, all that square root right there, all right? So this equation's good to go. You can do the unit analysis step next, and I'll help you out with that as well, too, to prove that this is going to be good. So check it out. For our unit analysis, I'll start writing it up here. So I'm just going to rewrite that equation we had before so we can keep it in mind. We saw that delta t is going to be equal to the square root of 2 times your delta y over your acceleration in the a, okay, acceleration in the, y component. So when we're solving for it, the variable, because for time, the units of time when I'm looking here, I know this is for acceleration, but I see seconds here, speed, I see seconds, so our time is probably going to be in seconds as well. So for our unit analysis, I'm going to say time is going to be in seconds. And then square root 2, that's from our equation, so 2 we're not going to put in here because we're just analyzing the units. That's why it's unit analysis. So the 2 I'm not going to be putting in my unit analysis. It's important for solving it, but we're not going to put it in. So my delta y, the units on it, are meters divided by our acceleration to y. As we saw in our diagram that we put here, acceleration is in meters per second squared. So I'm going to put my meters per second squared. And remember, when you're doing unit analysis, it's usually pretty wise to stack your fractions like this, okay? You see how they're all stacked? I'm not doing the slash to save room. I know you all like to try to do that to fit everything onto one sheet line of notebook paper, but doing this will make your life easier, and here's why. So remember, when you have, dividing by a fraction here, I always suggest that you multiply by the reciprocal. And so that means flip the fraction and multiply by it. So when we rewrite this, this becomes seconds equal the square root of meters over 1, because we took this fraction, we're going to flip it, multiplied by seconds squared over meters. Okay, so when we do that, see how these guys are the same diagonally? We're going to cancel those out, and then when I clean up this guy, we get seconds equal to square root of seconds squared over 1. Okay, and so since seconds is squared and we have the square root, this becomes seconds equal, because these guys cancel out, equal seconds. So our unit analysis is good. So all you'd have to do now is then do the substitution and solution for your time. Once you have your time, folks, you're going to go ahead and take that time from back over here, and after you do unit analysis, you have to do algebraic manipulation first to isolate time. Then you do unit analysis. You'll be ready to do the substitution where you plug in for time, all right? So from here, it's pretty much all downhill. I'm pretty sure you can take care of it, okay? So if you need more help in that, come in and see me one-on-one, please.